Thank you very much for the invitation and talk a bit about the work we're doing at Livermore. So I want to start motivating a bit why we're doing this. Probably if you think of matter at the nanoscopic scale, you think atoms and like these little balls connected with like sticks. But actually what we are interested in are not exactly this model, but something a bit more realistic, which is the electrons. So if you really look at this, you will see you have the nuclei, and then you have a cloud of electrons around the nuclei that more or less look like this. And the important thing about electrons is they are first of all, they are quantum particles. You cannot think of them as like just little balls, but a better model is about a cloud that surrounds these atoms. So they are really quantum particles. And the important thing is many of the properties we're interested at the atomic level come from these electrons. So it's something important to understand the behavior of these and simulate it. And for example, to motivate this, when you have solar cells, in a solar cell, what's happening is the electrons will capture the light, and they will convert this. The dynamics of this electron will capture the light and convert it to electricity. So, for example, to understand solar cells, it's very important to understand what the electrons are doing inside matter. And in particular, we're interested in something called electron dynamics, which is the simulation of electrons as quantum particles and study what is the dynamic behavior, how they move inside a material. And for example, some applications we can do. So, for example, as I mentioned, study interaction of how these electrons interact with matter. Here we have a molecule, a benzene molecule, and we put a laser field, which is essentially oscillating electric field. And you can see this green is the electronic cloud. These are represent the electrons and how they are moving with this oscillating electric field. So this is a very basic example. It's kind of the most basic kind of simulation we can do. And from this type of simulation, for example, we can get a light absorption spectrum. We can model how these systems absorb light. And well, there are some equations how to do it, but the important message is if we want to understand matter and how this matter will absorb energy from light, we can simulate this by doing this type of simulations. Another type of simulations we can do is atomic collisions. So, for example, in this case, we have a methane molecule and we have a proton, and we want to study how the collision of this proton moving very fast, how it interacts with this molecule, how it's deviated, or something like that. And in this case, so we have to follow how again, you see in blue, this is the electrons and how they transfer between the particles and how they react. And this is properly describing these electrons, in particular, these electrons, you have to allow them to be excited, determines how this proton is deviated in this collision. So again, this is another important example of what we can do. And this is another one. Oops. I don't know how this works. This is actually an example from Alfredo Correa, who is here. This is electronic stopping. So the idea is you have some material, for example, copper, and it's hit by a very fast particle, in this case a proton. And you want to study how the energy from this particle is deposited in the material and how this particle slows down. And this has many applications, for example, radiation damage, what radiation how can it damage materials. For example, if you have a nuclear reactor, you want to know how the walls of the nuclear reactor will degrade with time. You can do this. Or other medical applications, for example, proton therapy. We have a postdoc that went now, and he's working in the biomedical field because of his expertise in these kind of simulations. And in this case, again, it's the electrons. This particle is very fast, so it's the electrons that slow down this particle. So we need to really, if we want to study this computational, we really need to simulate the electrons in the material. And again, this is representing the what the electron, what the charge is doing, electron charge is doing in this case. And this is another example. This is we are studying the conductivity of metals under high electric field. So in this case, this is the liquid aluminum, and what these lines represent is the current, the electronic current going through the material. And what we can see here is how at the beginning we have the current, and then this current starts to decay. We give an initial current to the system, and then this current starts to decay. And we can see how the current starts to become more disordered as the current decays. And we find that actually the current goes to zero because the order of it becomes all random, chaotic, and so the average current becomes zero. You can see here, this is the current density as a function of time, how it decays. And we can do this, and we can study the nonlinear conductivity. So what happens when we put a very high current in the system, and we can see how the conductivity that is your typical Ohm's law starts to change, and as you increase the intensity of the current, you can see that first the conductivity decreases, and then it starts to increase. So these are all examples of simulations we have done, and all example of application we can do with this kind of simulation codes. The problem is these are very computationally demanding simulations. As we said first, yes, we cannot just use little balls and simulate little balls. We have to simulate fields over all space, and one of them for each particle. And we need to account for exchange correlation effects. So this makes simulations that are very costly, typically scaling at least with the square of the number of particles, or cubic with the number of particles. And we have to do very long simulation times, especially if we want to follow the ions. The ions are much heavier than electrons, so they both move at different time scales, but sometimes we need to capture these. So we have these very fast particles that we need to combine with the slow moving ions and do long simulations to capture all these time scales. This means we need very efficient codes that use computational time well, and also that make use of modern high-performance computing platforms. So we need to use GPUs, we need to use supercomputers. So it's a challenge from the point of view of code development. And the computational, the basic theory we use is called density functional theory, or time-dependent density functional theory in the case of doing time-purpose solutions. That is a computationally tractable method for quantum simulations. If you try to solve the Schrödinger equation, the cost is exponential with the number of particles, so it's something you cannot really do. So you need to do some sort of approximation, and this is density functional theory. And it's a very important application. It's estimated that around 50% of the supercomputing time in the US is used by density functional theory codes. So it's a quite important application in terms of like what people is doing for research. The problem, well, the scenario right now is most DFT codes are kind of they have a lot of legacy. They have been around for 20 years or more. They are very important. That a lot of the success with DFT, we go to this 15% supercomputer time, is because there are these codes that are very good at what they do, but they have a lot of baggage and a lot of legacy. So, and in that time they have become quite large. So there are these big kind of static things that are very hard to change. And in one of the main challenges is, as GPUs came, these codes were designed a long time ago. Many of them were done in Fortran, and it's very hard to just take that code and convert it to GPUs. To run on GPUs, it requires a lot of effort and breaking stuff and things like that. So in this scenario is how we started Inc. Which is a project that started around 5 years ago. And it's funded by the US Department of Energy. And when we presented this project, one of the things that DOE said was, okay, we want a code that can run on GPU supercomputers to TDFT simulations, but one of our main objectives is you can run on these GPU supercomputers. Because there are not many codes can do that right now, and we have this huge gap where the codes we have right now cannot make use of the computers that are available. So one of the questions is, okay, what are another DFT code? As I mentioned, there are many codes that are around already. So why do we write another one instead of taking one and modify it? Well, first of all, if you want to integrate GPU support into a code, it's a lot of work. You have to touch a lot of parts in the code. You have to explicitly parallelize. Even if we take an existing code, it will be a lot of work, and we will still have to work in every part of the code. And we thought, okay, there are modern software engineering techniques that we can use in terms of modularity, in terms of how to develop a code. I will mention a bit about that. And we can use modern C++ as well to develop this code to make something that is compact, is easy to maintain. Most of the existing codes are written in Fortran or other, like some of them are C, but also like very old code. So we thought, okay, yeah, there is all these new things we can use and try to make a much better code than what exists. And we didn't do this just on like from backend. Our team has a lot of experience developing this code, especially Octopus and Qbol. So we had all this experience, so we can say, okay, we have seen this code for a long time, how we can just start from scratch and do it in a much better way. And while the physics of Inc, I will not get too much into this. It uses plain Wave and pseudo potentials. And in general, we try to use the fairly standard algorithms that have been used by the community. So we didn't innovate at this point in terms of algorithms and stuff like that, because we're also trying to get the code running and focus on like a different way of doing things, a different way of writing code. So we started with the basic algorithms that are true and tested. One advantage is we have a code that is very easy to modify, so we can in the future decide, okay, we want to try this no other new thing, ways of doing things, and we can try it. And of course, one of the most important things is we have this new code, we have to validate and check that it gives the same results that other codes do. And we did this and get like same results as Quantum Espresso, for example, or Octopus. So we're good there. So a bit about the code. It's it's a clean design from scratch, as I said. And it's a code that is a fairly complete DFT and TDFT code in 23,000 lines of code. For comparison, most codes called Qbol, the code we're replacing, that has more or less the similar features, uses like 70,000 lines of code. And other packages are always like Octopus is 250,000 lines. Other packages having it is at least 1 million lines of code. So we are doing things much more efficiently. And which means our code is much easier to maintain, develop, and upgrade. It was written from scratch to run on GPUs and parallelize over MPI. So distributed parallelization of MPI. We'll mention this a little bit further. And it has testing for all the components. We have like from this 20 line of code, like at least 9,000 lines of tests. That makes sure every component is working properly. And in general, it's a modular and extensible implementation, so we can change things, and we try to break things into parts that make it easier to develop. So this is what I was talking about, the modularity. So Inc is like the main part that has the physics in a way, the DFT physics. And we depend on different libraries to do all the things. So we have an interface for doing MPI. A very important library is a library that Alfredo wrote is called Multi, another library to handle multidimensional arrays in C++. That is aware of GPUs, so can handle memory in GPUs, and can use accelerated libraries behind the scenes. So we can transparently have arrays that work on the GPU, on the CPU, and that behind the scenes can use these accelerated libraries, and depending where we are running, use the best available option. Okay. Then we have something called GPU run, that is a wrapper to run code on the GPU, code that is not covered by libraries and stuff. I will mention this briefly. And other specific libraries, for example, pseudo-potential parsing, handling, we have another library we'll mention a bit. Another external libraries that do things that are available from other people that we can directly use, and we don't have to write ourselves, like libraries for exchange correlation functionals or to handle crystal symmetries and stuff like that. And the advantage is all these components are independent. They have clear boundaries on what they do. They are good at doing one task and one task only. And they can be shared and reused. These libraries, for example, are used by other codes like QFCPack. So we have, we can share the development effort and have libraries that are very robust because they are used by different code as well. An example of this is this library called pseudobot, that what it does is parses pseudo-potentials files in different formats. So when you do this kind of atomic simulation, you have something called pseudo-potentials that are some sort of approximation of the potential of an atom that we can use for simulations. It's not very important if you don't know what pseudo-potential is, but the point is you have to get these files. And of course, as typical, they come in many different formats with different information and stuff. So the task of taking one of these pseudo-potential files and converting it into something the code can use requires a bit of effort for the different formats and stuff. And also they come in different sets. So people have been doing now sets of pseudo-potentials. So the idea of pseudobot is you just ask, give me a pseudo-potential for carbon, and they will give you a pseudo-potential and use it from one of these sets. And it does other tasks like pseudo-potential filtering, for example, that is necessary to improve convergence of code. And it has GPU support as well. So you can get your pseudo-potentials in the GPU, and the operations that you need to do with them can be done in the GPUs. Another important part of the code development is using Agile, the ideas of Agile. So working with things that we can really test, and starting from very small components that are well-defined, do as tasks. Maybe it's not the task we want, but with a task we can test, and start with something that works, and toward development, moving in a space of things that are work and useful, instead of designing code for 3 months, just thinking about different components, designing for 3 months, and come back and try to merge them all together and realize, oh, this is not what it works. It's not the best way of doing things. So just moving through a small task to find out what's the best way of doing things, and always keep testing. And this is the other idea that we have this test-driven design where if you have developed this kind of code, you can implement something in an afternoon and then spend 2 weeks debugging it, because there are if things don't work, it's very hard to find what is not working and stuff like that. So the idea is, instead of doing that, we write small pieces and we test those pieces, so we make sure each time if all the component we have is working, so it's much easier to figure out what's wrong, what's broken. So we write the code and the test together, and we use unit tests and integration tests to make sure this is always working. And these tests are integrated into the development cycle. So each time you make a commit, we test that all the tests are passing, and we cannot let anybody integrate tests into the code if they are not passing all the tests. And also we ask when you integrate a new feature, it has to be tested as well. And as I mentioned before, we use C++ to make a code that is simple and easy to write and understand. So for example, this is an actual line of code you will see. Typically, the Hamiltonian is one of the basics concepts in a DFT code. Typically, if you look at other codes, they have a Hamiltonian function that has, 10 arguments, different things and stuff like that. and you have to pass the input and the output, and it's very complicated how to call or that. But instead, in Inc, you have, this is actual code you can find, like, yeah, I want to calculate the Hamiltonian of phi. I say h phi equals the Hamiltonian of phi. And the advantage of this is that you make a code that is very easy to understand. It's very easy to write. So, for example, implementing TD-DFT in Inc took like 2 days or something like that, because the code is very simple. It's like just the things you need, express the formulas and not other things that are not clear. And the advantage is using C++, we can do this with no performance penalty, no hidden copies or stuff like that. Another example, for example, something that can be very complicated is when you work with crystals, you have this thing, you have Cartesian vectors, you have contravariant vectors and covariant vectors. And a lot of bugs come because you are in the wrong kind of coordinate system. The advantage is in C++, we can include this information into the type, but check the compilation time so you don't have no overhead into the data. And for example, we avoid, if you want to calculate the dot product, there are combinations that are not valid, or you cannot do them directly without knowing the metric of the space. So for example, if you do a dot product between two Cartesian vectors, the code will compile and it's okay. Covariant with contravariant is okay. But if you try to do a Cartesian with a contravariant, the code will not compile, will tell you, okay, this operation is not allowed. And the advantage is this doesn't have any performance overhead. You don't have to store any extra information with the vector saying, oh, this vector is one type of the other. Just simply as a compiler that takes care of this. So other part I want to mention that is important for us is the GPU support, because right now it's something that is fundamental in modern scientific code. Most of the supercomputers that are running, they use GPUs. So it's something we need to have. But it's a challenging, something challenging to do. The GPUs, first of all, they have this massively parallel processor where you have to write code that is explicitly parallel. They have an independent area of memory. And if you want to copy data to this from the GPU to the CPU or back, it's very expensive. So you really have to handle the memory as well and do it properly, because if you don't do it, you will kill all your performance just copying data between CPU and GPU. So how we do it? So the first thing is we take an everything on the GPU approach. So in some applications where you have a very intensive task, you can use what is called offloading. So your code runs normally, and suddenly you come to a part where you will do something very intensive. So you just copy your data to the GPU, run on GPU, and come back with minimal changes to your code. That doesn't work here. We have a lot of operations. We have a lot of data, so we cannot just keep copying data back and forth. So essentially, our approach was, okay, we're going to use everything on the GPU. We're not to store any data and this on the CPU. And the advantage is we don't have to copy memory back and forth. One of the challenges is now we have to store all the memory on the GPU, but in general, GPUs have smaller memory than CPUs. So we have to work with a little bit less memory, even though this is improving now. But one of the main challenges is we need to run all the routines on the GPU. Even routines that normally will not take any time or are not really important, they have to run on GPU, because if you run on CPU, it implies that you have to copy the data. And in fact, in DFT, most of the performance-intensive routines we can do it by vendor accelerated libraries for the GPU. So BLAS, essentially BLAS and FFTs, you can find at least for serial, for one GPU, you can find libraries. But the problem is there are other little pieces of code that you need to implement on the GPU. And these pieces of code are not, maybe they're not critical for performance or anything, but yeah, you need to write them on GPU. And this is what you do. And well, we also had to take other libraries that we use, like libxc and pseudopod, and implement GPU support in them. Not because they are very costly numerically, but because, again, we don't want to copy data to the CPU to call a library or something like that. So how do you program the GPU? So as I said, there are libraries that you can use to run on GPU. The problem is each vendor has a different library. There is no like unified framework you can use upfront, works everywhere. Well, for libraries and for the way of running code, writing the code. So CUDA, NVIDIA has CUDA, AMD has heap, Intel has different things, cycle or something like that. So we designed a small, thin agnostic layer that runs on the GPU, and we can compile for different architectures depending on where we're running. And also we can compile this code to run on the CPU, so we don't have to have a different version of the code, like a CPU version or a GPU version. We have just one code that runs everywhere. That's much easier to maintain. And even if you have the GPU version and CPU version, what typically happens is you fix something somewhere and suddenly, oh, I forgot to change it here, so it works differently, or you have to look at the parts. It's a mess. So yeah, I have tried, and yeah, it's complicated. So it's much better if you just have one single code. And what we use for this is first this multi-library that I already mentioned that takes care of allocating memories, doing copies, and GPU accelerated libraries. And we have this simple code, it's called GPU run, that does the custom kernels, the other little pieces of code we need to run, all the loops and stuff, and writing on the GPU. And behind the scenes, this is compiled for the different GPU versions. Actually, now we have NVIDIA CUDA and AMD. I forgot to put it here. We still haven't worked with Intel, but we have NVIDIA and AMD versions, so this code can compile and run on both the machines. But our code looks completely independent of what you're doing. And this is an example of how we do it. This is, for example, a kernel. This will be summing to matrices. This is our GPU run, so we use what I call C++ lambda, so a little function that we can write, and we just pass to this function that runs internally a loop, compile this code for whatever interface you have. If it's a CPU, it makes it into a loop. If it's in the GPU, we'll create a kernel and launch this kernel or whatever that function is. So that works, but when we are for syncing into a node or if you have a single GPU. And that's the easy case. The problem is this is not what we are targeting. So this is Lawrence Livermore next supercomputer that's supposed to be deployed this year. I don't know if that's going to be true. They have been saying 2024, and 2024 is kind of getting less time than 2024, but I assume that maybe in the beginning of next year. So this machine will have a performance that's still not clear, but it's going to be more than 2 exaflops performance. So that means it's going to be the fastest supercomputer in the world. But to use this machine has 20,000 GPUs. So to use this machine, we have to, on top of programming for the GPU inside the node, we need to do parallel programming. And this has what is called a distributed memory architecture. So this machine is essentially looks like a lot of different computers connecting by a fast network. So there is no shared memory or something like that, so we need to parallelize for this machine, and we use something called MPI, or the Message Passing Interface. That is a framework where you essentially run several copies of the program, and you have to explicitly send the data from one process to the other. Which means the programming is more involved, said, using threads or GPU programming, but allows much more control and much more efficiency in these machines. And actually, we know how to do this for CPUs. We have been doing this for CPUs for, decades already. And we can scale, we have codes that have scaled to 1 million CPUs using MPI. So that we know how to do. The problem is when we go to GPUs, there are new challenges and there are new things that we have to deal with. One of the problems is the communication is more expensive on GPUs. First of all, there was a big jump in terms of hardware when we started using GPUs. Suddenly, the processing power became like a factor of another magnitude faster, but networks didn't have that similar jump at the same time. So now the communication cost is proportionally higher. And the other problem is GPUs. We have this complicated architecture where we have a CPU with its own memory, and then we have a GPU connected with its own memory. So typically what happens if you just say, if you want to copy data, a lot of the time is you have to copy from the first GPU to the first CPU memory, then you copy to the network, to the other CPU, and then it has to copy back to the GPU. So it's a complicated problem. There are ways to accelerate this, but they don't always work well. So that still means that, yeah, we're in a scenario where the communication is more expensive proportionally to the speed of the processor. And the other big problem is there aren't many GPU accelerated parallel libraries. So for example, if we want to do parallel linear algebra, we can use ScalaPack. That has been, the interface is horrible, it was written in Fortran 77. But the code is there, it works, and a lot of people, are using it. We have implementations. But if we want to do parallel linear algebra on GPUs, there is no really a mature library we can directly use. We have to implement our own routines because there isn't really a library. There is people working on it, but of course this takes time, and it takes time for it to mature. Same with parallel FFTs, for example. There is no parallel FFT, fully robust parallel FFT library that can do this. So these are one of the limitations that we are having. We are having to write our own parallel version of these libraries that, of course, are not as performant and really require a lot of effort to tune and accelerate. So this is something we are waiting for to be done and have options we can use. Nevertheless, we can scale. You can run in parallel with the code. This is, for example, our weak scaling, so parallel graphic. So essentially, you can see the time per iteration for TDST iteration with the number of atoms, where we add as many processors as we need when given certain efficiency. And we can get to 1,500 atoms with time steps of less than 1.5 seconds. So this means we can really do, with these times, we can do real simulations with systems of this size without much problem. Ideally, we will want this to be flat, but there is this parallelization issues that I'm mentioning that, well, we still are not there. And this is a strong scaling plot. So in this case, we take a fixed size system. So in this case, 1,000 atoms of aluminum. And we try to see what's the speed up as we add more and more GPUs. And you can see that up to 128 is almost linear scaling, and then it starts to decay. But we can still, with a reasonable performance, get up to around 1,000 GPUs, which is impressive when you think that essentially you're running 1 GPU per atom in this simulation. So again, this is something you could do, and in a few hours you can get results with this kind of performance. So yeah, we can get good performance, but one of the important things for code is the user interface. We want our users to be able to use the code. And to be honest, 1 hour of computing is much cheaper than 1 hour of a researcher. So if we make the researcher save time, it's more important than if the code is fast. And again, as I mentioned, a lot of the codes that exist for this kind of things has what we call less than ideal interfaces. They were designed a long time ago. And a lot of them, again, with Fortran that has minimal kind of input-output capabilities and stuff like that. Most of the software, the way it's designed now, uses text files for input and output. So you write some text file in some format they decided. And then you will get the output in other format they decided. And some of them are very bad formats. For example, there is one code that you have to select an exchange correlation functional, and somewhere on the web they have a list. So if you want to select in the input file, you have to put a number. So you have to put one functional 123. So you have to go to the list and select the functional you want and put inside the file the number. And they have different conventions. With a negative number, it means something like that. And it's kind of, come on, I mean, converting a string into a number is a basic task any computer can do. Why can't you just let people put like the string there and what it means? But yeah, some of the codes are not that bad at that, but that happens. And that means that it's hard for users to learn, to write these input files, and it's error-prone. Some code is like, oh, you missed a semicolon and an ampersand, and the code will not run. And sometimes it happens, yeah, you modify something, send your job to the queue, you wait for 8 hours just to get back an error. There's a syntax error in the input file. So, yeah, it makes things hard for users. And the other problem is these days people are running a lot of simulations, not just one. So usually what they do is they write scripts that run simulations, analyze results and stuff like that. And users have to write something that generates an input for this code and then passes the output and looks at the different like format of the code and oh, what is here and oh, I have to skip this line or not or whatever. And then they come with a new version where they just change another line to that thing and your parser breaks. So we feel that this doesn't work properly for users. And we have been thinking, okay, what to do, how we can do this different. And we came up with this idea. It's not something that's set in stone. It's like a different concept and something we want to try, see what users think. I mean, we are researchers. We're trying to research how to make the best code, so we have to try things. And the idea we have now, instead of having this input file model, it's your simulation is just one directory or one folder where you're going to run. And your data is the simulation data, simulation configuration is persistently stored in this directory. And you have commands that you can run and modify the data, the simulation configuration in your in this directory. So you have these commands that access the data, and you have both shell, command line, Python interfaces to modify the code. And this is for an example of how you do it. So you create, for example, a directory. This directory is where you are going to run the system. So your directory, your folder is the system where you're going to run, which matches that what a lot of people do. Like when you run a simulation, you create one directory for that. So we're kind of just taking that and doing it mandatory in a way. You enter the directory, for example, and you say, these are all commands. You say inc ions file, and this file contains all the atomic positions and all the information. Then you set up the cutoff. That is the only required parameter you have to give for the simulation. Ideally, in the future, you won't have to give it, but for the moment, you have to set it. And then you can say, okay, inc run ground state, for example. And this is the function that will do the heavy work. It will run the ground state calculation. And this is separated from the rest. And what you can do, for example, is you set up your simulation here. You can query and see, oh, is my simulation set up correctly and everything. You have your directory ready. And then this is the part you submit into a queue to the supercomputer. The rest is very quick, so you don't have to worry about running in a queue or anything. And this is the part you do. So your simulation is set up. You don't have any problem with syntax errors, because if you have those, they will happen before. And you can exactly see there are commands that tell you exactly what the code is trying to do. And to get the results after you run your simulation, there are commands that return the result. For example, if I set this command, it will give me just a number. This is the total energy. So, for example, if I'm in a script, I can just run this command and get this value without having to parse anything. I just have a numerical value. If you want the forces, you can say I want the forces, and it will give you all the different values. Or if you want value, you can also query the specific value. And we also have a Python interface. The Python interface is called Pink. That essentially is the same commands, and they are interchangeable. You can run part of your commands in Python, part of your commands in the shell line, because all the information is persistently stored in your directory. There is no code objects that you have to worry about. And in a sense, your object is the directory we're standing. Of course, this limits a bit what things you can do. You can think of more sophisticated stuff. If you want to do that, there is also a C++ interface, a library, a library where you can do much more powerful stuff. But for end users, in general, this is much more simple to do. And it is the same idea as before. You can set simulation parameters and run and do that all this from Python. And in the case of Python, for example, your results, you directly parse your result as you get directly a Python array with your results. So this function will return, and this will be an array with the data you want. And if it's the energy is just a Python variable, so you don't have to write parsers or do any weird stuff. Just get your results in the native language format. And in general, I think the basic stuff is we want to focus on user experience. We want to make the code as easy as users as possible. For example, the installation, we want a code that is easy to compile and install, because this is normally a big issue for users. You can spend days trying to compile one of these things, especially in supercomputer and stuff. Also provide documentation that is easy to access, easy to get, and it's good documentation that is up to date. In ink right now, a part of the commands, you can type ink help and it will return help, and the command you want, and it will return the help. So you can read directly there from the terminal or from Python. You can read, oh, this is our option, what is available, and stuff like that. Another important thing is the idea is the code has few options, and the default values are smart. So the idea is you should just specify the physics of the simulation, not specify what's the algorithm to solve or whatever, because that's not your job, and that's something that the code should be able to do easily, and that has to do, and the idea is, whether setting the best default values or having some time of heuristic if we need, for these systems, let's try these options. And that connects to the idea of having reliable and robust algorithms. One of the biggest issues with this in DFT code is converging the ground state. You have a lot of different parameters that you have to set. So we want to have something that's reliable and robust that will converge in most cases, so you don't have to spend time trying different combinations of parameters and stuff to find something therefore. Of course, this is not something easy, and it's an objective. It's not something we have right now. But it's a philosophy in designing the code. We want it to be easy for users. And it's something that many scientific code developers forget about. Because you know the code very well. So for you, it's super easy. But for the other people, it's not. And just to conclude, we think this is a new approach to the electronic structured code. We are doing things differently in ways have been done. Of course, there are other people working along the same lines. We're not saying we're the only ones thinking about it. Here, Michele, for example, is working on using Python as an interface for codes and stuff like that too. So I think it's a movement that's happening. But there are things we have to think, and I think we're missing there. For example, the user experience part is something that not many people care about. And of course, it was in progress. There are a lot of features we're implementing. There are a lot of things we have to put in the code. It's a lot of work. But we're doing that work. And the first paper came out in 2021. Ideally, we'll get another one soon. Just to finish, I want to say, the idea is this to be a code that is available to the community. We're open to people contributing, and it's not something that we want to be just our effort. We're happy to have other people contribute to the code. It's distributed under open source license that allows the code to be used and linked by other packages without restrictions. And all the development happens in the open. It's available here in GitLab, and everybody can contribute if they want. And that's all. Thank you very much for your attention.
think we have 10 minutes for questions. Oh, sorry, go ahead. I think we can go students first.
Yeah.
Yes.
So it's a very nice presentation. I think we all enjoyed your presentation, the way you motivated and came to the problems and challenges. So yeah, it's clear that there are lots of work, and you are transforming the legacy code base to the updated one, useful one. So my question is like, how do you manage the community? Like, how do you attract the community to work into this problem? And how do you think, what's the future plan? Will it become a legacy code base in 10 or 20 years? So,
well, hopefully not.
Yeah.
Part of the thing is if you have a code that's smaller, it's much easier to update. If you work on like high level abstractions, maybe if they say, maybe in 10 years, it will be like FPGAs or whatever, or a different paradigm, and nobody will run on GPUs. We think we have a good abstraction level, so things can be updated. Our code looks like the actual algorithms, not like how we're running behind the scenes. So hopefully that's something that the code will be available. It's something we are thinking about just to start, but we don't know yet. But obviously, if you have 20,000 lines of code, it's much easier to update than if you have 1 million. With respect to the first question, well, it's attracting people to develop and use the code is not easy. Most people just use what they're accustomed to. We think like GPU support is one important aspect. And we try to make it the improving the user experience is also something that attracts people, and then start using the code and developing it. I don't know if there is much more that we can.
Oh yes, I just lots of questions together. Yeah. Thank you. Great answers.
Donna, you had a question?
Yeah, I just was curious about your experience with different GPU vendors. And have you, I hear of people doing these interfaces to different GPU vendors, and I'm wondering just how easy that is and what kind of experience that is. And do you, have you found one works better than the other, or?
Well, NVIDIA has the advantage here. They have been doing this for much longer than anybody else. In general, it's much easier to work with NVIDIA. They have a lot of ecosystem and libraries. The others are playing catch up. AMD, they are really kind of new to the game. There are a lot of things that they don't have, or they promise, or they have libraries that should work, but they don't really work and stuff like that. But in general, the basic, kind of the syntax and how to do things is very similar. The issue is more like the software is not as mature as the one that NVIDIA has. Porting is easy, but then making it work, it's kind of the hard part.
And El Capitan, what GPUs?
It's AMD.
AMD.
So.
Oh, okay.
Yes. So DOE has this idea of like, they don't go, we want people. So NVIDIA got a lot of supercomputers, and then they said, okay, now we are going to give the opportunity to Intel and AMD, because they don't want they want to have competition and have different options. So, yeah.
There was a question on the back.
So first of all, thank you for your presentation. It was really good. So I was thinking, very similar to this question, in a long-term period, how do you plan on managing it? It's open source, so it's good. It will be community-driven, but do you plan on putting a control over it, or how do you plan to do it? And another question is, have you tried it on a smaller scale, or do you have a backup for it? And the third is, have you tried introducing artificial intelligence in?
Well, first of all, we must be one of the few programs that remain that don't have artificial intelligence. We haven't really done anything. I think the place where we could use some artificial intelligence is an interface. Maybe it's having something like you say, hey, whatever you are called, run a simulation and I don't know, I don't know, like cubic iron or whatever, and the code will just understand what did you mean and will run and give you a result. That will be an interesting to do, I think. But it's not something we are doing. So the other question about the community, it's a hard problem. Like it's a problem in itself how to manage large software packages. In general, you have to have some. I feel you have to have some kind of centralized group of people in charge of accepting and guiding the larger development group. Otherwise, the code quality goes down. Because people are interested in solving the problem, they're not interested in the big picture of having a code that's scalable or something like that. So you have to be able to tell people, your code is great, it works great, but please add some tests, clean this up, remove the comments on your gotos or whatever. So, yeah.
Definitely, you will need some moderators.
Mm-hmm.
Yeah. Thank you.
Please.
Yeah, so you did mention that you are not using any like kind of shared memory, like basically everything is distributed. So I'm just wondering, is there any overhead cost for not having shared memory, or maybe in your specific just distributed?
We cannot use shared memory in like this big supercomputer. So with shared memory, at most you can scale. Like if you had a machine to hundreds of nodes, I don't know if there's still machines like that anymore. But in my experience, actually, a well-done MPI code takes more effort to do, but ends up being faster because the communication is something you are explicitly managing. In shared memory, you are kind of like, you don't know where the data is and you touch it from different CPUs and stuff. Here, it's with distributed memory, your communication explicit, you have managed it explicitly. So in a way, it's a much more valuable resource that you manage better. But of course, the cost is it's harder to develop the code. You have to explicitly manage the communication, stuff like that.
Any? I was curious about if you use like mixed precision in these things, single precision, double precision, to try to reduce some of the energy costs of this, or speed up the calculation in some way. Is that?
Yes, it's. We haven't really tried it. It's something we'd like to try, especially now. With these GPUs, there was a time where they started having double precision, and it will look great. Like, they're just having double precision at twice the cost of single precision. It's nice. Then machine learning came along, and suddenly NVIDIA was like, we are the machine learning company, so we can use only like single precision or half precision or quarter precision or whatever. So now again, we're in this scenario where it will pay to have single precision. We haven't really explored this. It's something, we would like to consider. Certainly in C++, it would be easy to do in terms of where everything is a template and data and stuff like that. But we haven't really explored. In general, these codes are not easy to run in single precision. Some people are doing it, but there haven't been somebody that says, this is the way of doing it. So it's something we will have to learn ourselves. Okay, what can be done in single precision? Where do we accumulate that precision and stuff like that? So.
Yeah, Dennis?
Yeah, I wanted to understand what you meant by pseudo potential filtering.
Mm-hmm.
Does the user have to download the pseudo potentials and store them somewhere, so that they just pass on that? I need this kind of pseudo potential for this type of system, or do you have them in your I just have to state it so that you understand?
So the idea is, you have pseudo potential files, but in a code you have to use going from that file. In the code, you just want a function that says for the value of this pseudo potential for r equals 1.3 is what. So that's what pseudopost does. It kind of reads the pseudo potentials. The simplest thing is you give it a file and it will give you a thing that you can ask as a function where you can ask what the value of the potential is in each point of space. And the problem of that, there is a lot of different things. You want to read different formats. Even the same format, some files have some type of information, others have other types of information and stuff like that. Then the other task is they, like, people don't give you one pseudo potential, they give you like pseudo potentials for most of the periodic tables. So what pseudopod can do is you say, okay, I want pseudo potential for carbon using the SG15 set, and pseudopod will take care of everything, like giving you that information. I don't know if that answers your question.
Yeah.
No, thank you.
Any more questions? Nate?
I have a question on, so you're talking about how there's GPUs and CPUs, but from what I understand with El Capitan, it's going to be an APU, right? So the CPU and the GPU are
Yeah, the memory is shared.
So is that, would that accelerate things probably, right, for the code? And is there kind of like change in your thought planning that would have to change for systems like that as they come online?
Yes, a little bit. I mean, our approach to doing things works. The main difference, we don't have to worry about the memory copies and stuff like that. But we still don't want to use the CPU because it's much slower. We made the effort to run on GPU. And something that probably will happen in the future is supercomputers now, there is a lot of people using the CPU, so they have to have fast CPUs. But maybe in like the next generation of computers will have a very tiny ARM GPU, ARM CPU integrated in CPU that really cannot do much computing. So we got to a point where we don't care what the CPU is doing. It's just a scheduler for the GPU.
Okay. I think it's time to wrap up. Thank you again.